So welcome everyone to this first webinar that we are doing from IACE. So the first clarification I have to do is that this webinar will be in English. So you'll see we'll be organizing some webinars from IACE, from Spain chapter of INCUSI. Some of them will be in English, some of them will be in Spanish. This one will be in English. Just to explain a bit, so IACE is the Spain chapter of INCUSI. So you are probably already familiar with INCUSI, the International Council for Systems Engineers, and IACE is the local chapter here in Spain. So today we are going to have the pleasure to have Santiago with us, who will talk on the topic of predictive maintenance of machinery, manufacturing lines, and vehicle fleets, Industry 5.0, digital twins, and simulation of strategic assets. So first, big thanks to our CAP members. So CT Engineering, the company where Santiago is one of the CAP members. So we want to thank them because without them, this wouldn't be possible. Then quick reminder, we have a new board in IACE from January this year. So it's quite an active board. So I invite everyone to reach to us if you have any suggestions or anything they would like to do with us. This webinar is part of what we do. Other benefits we have for our members, of course, includes all the INCUSI benefits. So access to all the publications from INCUSI and IACE, the system engineering professional certification, webinars and other face-to-face events, working groups, both at INCUSI Global. So there are lots of working groups, and also we have some local working groups here in Spain. Namely, for example, MBSC is quite active, requirements, volunteering, etc. And also of course, the possibility to join the professional system engineering network of INCUSI. So I leave here the links in case you want to join INCUSI for those that are not a member yet. Just moving into the topics, before moving into today's webinar, I just want to introduce the one we'll have in 2 weeks. So this one will be in Spanish. So feel free to join it. You can do it. You will find information also in the website. So if you look in the IACE website, you'll find the link. You can also scan this QR code with your mobile phone to go directly to the registration link. So in that case, we'll have mission engineering for systems of systems by our MathWorks colleagues, Maria and Luis. Okay, so just moving into today's topic. Again, predictive maintenance of machinery, manufacturing lines, and vehicle fleets, Industry 5.0, digital twins, and simulation of statistics assets. And this will be presented by Santiago Ferrer, who is one of the referent system engineers here in Spain with more than 20 years working for different industries. So please, Ferrer, Santiago, it's all yours.
Okay, so thanks a lot, Alberto, for the intro. So first of all, please let me share my screen with all of you. Please let me know if you see my screen, please.
Yeah, it's not full screen, but it's okay.
Okay, so I'm going to try to get the full screen. So yeah. I think it's okay. So thanks a lot, Alberto. So good morning, first, ladies and gentlemen. This is Santiago Ferrer, PM of the City Engineering Group in Spain. And thank you so much for the given opportunity to be with all of you and present the capabilities of digitalization, simulation, and virtual twins onto the industry, from civil engineering to manufacturing, and also applied to smart cities. So for me, believe me, it's a real pleasure to be here. We are following this index, starting with a general vision and fields of use of digitalization applied to industry, the model-based systems engineering concept, the performance of virtual twins, its benefits, of course, and when changing gears to smart cities, I will show you some examples. So let's start. So we start with a general vision of CT as a company. CT is an international group based in Europe, a leader in technical innovation, design, manufacturing, support engineering, and R&D. City provides services in the aeronautical, space, naval, automotive, railway, energy, industrial plants, and architecture areas. So we are 2,000 people spread across Spain, Europe, and India, with 25 offices and 48 business units. And here we see an evolution of all of our ISO certifications that we have achieved over time from 2001 to the present. As the most important ones, the ISO 1901, 14001, 9100, 27001, and 45001. And now going to the business, our first thoughts regarding digitalization goes to industry and manufacturing in particular. So it's really a good starting point, but not the only one, as we'll see in a few minutes. Think about a smart city example. Industry 4.0 is based in automation and digitalization, big data to the benefits of productivity. But Industry 5.0 is based on a human-centric approach. Human beings are the main beneficiary of technology, of digital twins, and artificial intelligence to help us making the best decisions. Regarding product engineering, as we see on the screen, we can use the virtual world to first the conceptual design and specification. So we can come up with our first ideas in a computer and see from the start the foreseen performance of the item, components, or assembly we are designing. Even we can know if we meet the specifications according to customer requirements and legislation. So everything from your PC or laptop. Systems engineering and structural design from the hardware and software standpoints. It's possible to complement our design with all the ancillaries attached to the system. From the hard and software standpoint, the simulation and coordination between all components and subsystems. So it's a virtual testing, and here is when the concept of a digital twin enters in. A complete simulator where all environments can be applied and being duly simulated in an unrisky and cost-effective way. A full-scale replica taking and giving information from all the elements active in the scene and connected via IoT sets. So now 5G communications are going to be instrumental, and according to some sources, 6G, not 5G, but 6G is about to be born very, very soon. Mechanicals, electricals for vehicles, for smart cities, and for factories. A complete city, a complete manufacturing plants can be replicated virtually with all participating elements. The engineering of full vehicles, data transmission, and the general working condition of any machine and processes we can come up. Of course, design, verification, validation, and final deployments. So virtually speaking, we can test everything to its limits and see the maximum capacities of systems, vehicles, factories, and even a complete smart city. So in one word, so we talk about the simulation of all processes via digital twins as virtual replicas, the virtual reproduction of a complete system. Thinking about manufacturing engineering, the virtual approach can be applied to, first, the process engineering, manufacturing lines, and tooling simulation. So all kind of processes, lines, tools, and stations can be simulated to the slightest detail. So it's very important to remark the simulators and the digital twins can get information not only from the real world, but also they are able to generate its own virtual data replicating the reality. So that's really important as a mean to train artificial intelligence. That's the core of a digital twin. The algorithms are specially designed to learn by themselves and able to adapt and change their logic according to the input they received. Of course, the supply chains management, quality and inspections are included in the concept of Digital Industry 5.0. Think about, for example, computer vision and its capacity to identify objects and especially faults and effects of any kind. So it's very especially important in key sectors such as aviation, electronics, and so on. So a digital twin is able to foresee and predict the circumstances and risk environments much before they happen. So it's also important to remark the approach to predictive maintenance for vehicles and assets. So how good is to know not only the operational condition of assets of any kinds online and in situ, but to know in advance its evolution and exactly when a likely breakdown can occur. So all measures to avoid these fall downs can be applied in an early stage, saving a lot of time and money and improving the user experience and customer satisfaction. And now, regarding systems engineering, one of the strongest points is the digital twin and the capacity to simulate all types of industrial processes and assets applied to the industry and to everything. Among the general solutions, we highlight the real-time simulators applying a system architecture based on models, so what we know as MBSE, making possible the communication between different systems in real time through IoT devices. So with this approach, it's perfectly possible to come up with training devices, developing system models of user applications with powerful graphic engines such as, Unity or Unreal. So it's possible to integrate any solution that may be already in the customer hands while combining simulated and real systems in a hardware in the loop approach. Also, test benches can be also considered. So here we see, as a matter of example, an electric motor, a physical asset linked to a virtual urban bus. So I mean, the combination of real assets with virtual environments perfectly match. And continuing with the technology deployed, also we highlight the capacity to generate synthetic data from simulations for artificial intelligence training. So we do cooperative simulations, integrating simulators from different platforms. We are capable of carrying out mission and capabilities training in the military fields as well as the civil one, and simultaneously with the help of a platform to gather all inputs from different kind of simulators. So we are capable of making digital twins according to the LVC approach, I mean live, virtual and constructive, linking real entities, live, with simulated and virtual environments, virtual, and in a constructive approach to introduce new and changing environments. So finally, we do final validation work with the customers. And as core competencies, and also as a very important remark, so we need to develop software of any kind, including user applications, databases, user interfaces, and communication between systems. We need to model any system applying deep machine learning, virtual models, and digital twins in real time, acquiring telemetry data from machines and vehicles via IoT. So here is where it comes into play, the capacity to predict exactly what's going to happen in the future, establishing tendencies, trends of behavior, and setting the field of predictive maintenance. Additionally, we can combine 3D tools from other companies, so it's possible to get accurate replicas of testing grounds to replicate testing conditions and the real life of assets and machines. And also it's also a good idea to combine the display of information using augmented reality, superimposing virtual information to the real world. And last but not least, also, it's possible to link applications related to virtual reality to enhance training and coming up with an immersive experience, improving really the user experience field. And in the terms of design, we can develop cockpits and ground control stations with HMI for industry in general and vehicles in particular, with which we have already entered the area of hardware developments, helping validation with end users. So this can be linked to remote operation and automatic driving of machinery of all kinds, acting the human being as a supervisor. So we'll see later in a few slides. Also, we should be able to perform the design of systems and better to say systems of systems. So we have to remind any systems and subsystems in any asset is linked to another one, making up a whole assembly, working as a one and only entity. Now comes into the middle the micro design of electronics as well. And also this contributes to the final stage of validation and verification, what's called as V&V, in unison with the final customer. And to conclude the chapter regarding systems engineering, I would like to mention a small array of transversal skills it's useful to develop. So I mean, firstly, the capacity of integration as being one of our capital know-how. The ability to make the conjunction between different systems from different suppliers and different platforms. This enables us to certificate any system in front of the final customer and to perform a relevant role when applying maintenance following a user manual. So on the right side of the screen, we see at a glance core competencies we have to observe if we wanted to get a full virtual ecosystem in our industry. So we go from conceptual design to cybersecurity, passing through simulation, digital twins, IoT, predictive maintenance, and final validation. So if, in one word, if we are able to embrace all of this, either by ourselves or with the help of partners, we're on the right path to draw the main advantages from virtualization. The virtual integration comes from the hands of visual engines able to generate 3D environments, and not only that, but also making possible the three most important challenges and capabilities for a virtual twin simulation. So I mean, the first, the hardware in the loop, introducing real assets into a virtual worlds, the software in the loop, introducing any solution into the main virtual twin, and finally, the human in the loop, introducing the humans into the virtual worlds. So please be in mind that the two most important powers of artificial intelligence is the ability of capturing and interpreting images, what we call as computer vision, and the ability to help us to make the most adequate decisions. So artificial intelligence is not going to substitute us, but to help us in our everyday work. Remember the approach of Industry 5.0, you know, the human-centric. In this page, on the right side, we can see the example I've chosen as an industry, making the virtual twin of its HVAC system, you know, virtualizing pipelines, compressors, and fans. So regarding predictive maintenance, it's for me, it's a very important asset and bonus in any kind of industry. So it's a set of actions necessary to keep machines running, minimizing unproductive times due to failures, machinery breakdowns, or unforeseen stops. So the main objective is to anticipate unexpected stops and minimize downtime. But predictive, not preventive, but predictive maintenance goes further. So by monitoring the production chain, we can know and control machine data such as temperature, humidity, pressure, activity times to evaluate and detect problems before they happen. So the use of artificial intelligence and deep learning allows for more effective and faster predictive maintenance management. So in the picture we show how artificial intelligence and machine learning work for failure prediction. So all this data, those captured in real time and the historical ones, can be used to improve predictive maintenance and for machines are used to learn and detect problems autonomously, displaying alarms indicating when a part has to be changed, or in extreme cases, preventively stop the production in order to extract information, extract the knowledge, and generate the predictive models detecting when a defect in production or in quality is going to happen. So artificial intelligence and cognitive technologies are used specifically deep learning algorithms. So to implement predictive maintenance, it's necessary to have algorithms that are continually and continuously learning and improving the models. So, and this is where artificial intelligence and deep learning algorithms comes in. And how it's possible to deploy. So first, all the data considered is imported and stored, performing the necessary transformations in them. So the second step is to carry out an effective exploration of the set of historical data prior to developing the models in which the variables allowing patterns to be identified are defined. So first we took out the variables. And once we have the model, we move on to the training phase, and when it's sufficiently tested, it is deployed in the real environment. So it works with the new data and carry out predictive maintenance, generating the necessary alerts, early alerts of failure or decreased in the quality of the parts we produce, or in the case the predictive metrics are far beyond the thresholds previously defined. So there are different combinations of neural networks, recurrent, convolutional, that can be combined to generate models that allow data to be processed in real time and provides failure predictions with high levels of accuracy. So the approach at the City Engineering Group is based on the use of neural networks and artificial intelligence algorithms to establish the predictive model by taking all the operating data of the assets to be examined and also taking into account other connected elements. So reaching this point, I would like to stop for a while and well, I don't know if among the audience, if there is any kind of question, any kind of interest, comments, if somebody can, asking a question or anything. Okay, so if there is no question, so we can discuss at the end. So we continue. And now going far beyond in this section, so we'll see what predictive maintenance consists of and how it differs from other techniques. So there are mainly three types of maintenance used now. So the first one, run to failure. So the maintenance interventions are carried out after the failure occurs. So it is used specifically when equipment failure doesn't significantly affect operations or productivity. The second one is the planned preventive maintenance. So the reviews are carried out to prevent the equipment from failing unexpectedly. So is, for example, in our car, the overhaul, the revision every 20,000 kilometers, example, and the predictive maintenance, in which case we need to control the performance of the equipment. Through IoT systems, we transmit the data, which is collected over time, allowing us to determine how much useful life remains for a vehicle, for a machine, for a part, for a component. So by anticipating when the machine will fail, so we avoid unnecessary maintenance or unexpected failures. So the predictive maintenance consists basically of four phases. The first one, the collection of system data. So we find two main methods, onboards and offboards. The first, onboard, consists of collecting data from the equipment using sensors, while off-board methods are based on the use of large existing databases. The second stage, the processing of data, due to we work with large volumes of information and data, we must eliminate irrelevant data and extract only the most important one. So this is especially important when we work with artificial intelligence, since the data we use to train the model greatly influences its performance. The fault diagnostics, the remaining useful life, RLU, is normally used once we obtain the inputs and the outputs from our artificial intelligence, so we can use them with a health indicator, allowing us to know the states of our machine and predict its useful life before the end. And finally, the decision of the maintenance strategy. And once we know the remaining useful life of our machine, we can make the corresponding maintenance decisions. So there are 4 models to implement the predictive maintenance. The first one is the physical one, the physical model approach, and it consists of a physical or a mathematical model of the system to evaluate component degradation. So to be frank, so it's very difficult to implement in complex environments. The second one is the knowledge-based approach that we use expert systems or fuzzy logic. So it requires expert knowledge to build the system. So it's not so much affordable in some cases. Data-driven approach uses computing power and a large amount of data. So there are 3 models. The first one is the statistical model, stochastic model, and machine learning models. And finally, the digital twin approach uses data and models, creating a union between digital and physical worlds. So the most widespread one is data-driven, using a wide variety of algorithms and applications of both deep and machine learning. Deep learning methods guarantee good performance in predicting failures, but require a large amount of data compared to traditional machine learning algorithms. And the digital twin is by far a modern technique, maybe is the best, with great capacity to identify abnormal conditions and predict the useful life of the product, being able to combine physical models to create the digital twin, and data driving, combining the information from both models. So our approach to predictive maintenance allows us to anticipate maintenance operations and failures before they occur. And in addition, we can design operations to improve any system. In these cases, the city engineering group is in charge for analyzing all the information available from any source, analyzing the root cause, carrying out functional investigations, developing model hypotheses, and identifying relevant variants and proposing validation methods. So in short, so we coordinate the developments of the entire system. So the case of Ecomobile 23, it's a good example of this. So applied in this case to an electric urban bus. We can imagine the complexity of connection with telemetry, its data transfer to a database, the predictive maintenance calculation, and the final ETAL twin. So ETAL twins interacting with each other. So in this particular case, at CT, we have chosen what we judge as the key elements of an electric vehicle. The electric motor, the battery pack, the ADAS systems for, in this case, the emergency braking, the air conditioning units, and finally, the wear and tear of brakes and tires. So we have done firstly a model of each subsystem, and once finished, the next step is to link every individual model in a one and only platform and play the interactions between subsystems. So we all agree the status of the roads or the style of driving can affect strongly the life of the battery pack or the tires, for example. So this implication is linked to the economical operation of the vehicle and their efficiency. And with the help of our capacity to predict what will happen to the vehicle in the near future, we can reschedule maintenance operations to best dates. We can reduce the stop times. We can optimize the availability of spares in a just-in-time approach, avoiding to accumulate tons of parts in thousands of cubic and square meters and saving a lot of that money. So as well as expanding the real life of the fleet of vehicles, decreasing to the minimum the stoppages due to breakdowns. Um, we have seen previously the advantages of predictive maintenance in this case, vehicle arrangements. So if we focus our attention to battery packs in particular, the battery packs can cause significant pains to public transport fleet managers. So batteries are at the heart of electric vehicles, and the performance and lifespan are key factors that influence the total cost of ownership of electric buses, and can make the difference between a successful investment and one that fails. So in this project, the objectives we have set are: first, provides the electrical vehicle manufacturers and fleet operators with information on battery quality, failures, and anomalies long before they occur. Developments of machine learning and artificial intelligence models that allow faster iterations. And this last point is very, very important, taking into account the vehicle data, not just the battery data, but data from all over the vehicle. So key influences in the case of a battery, as an example, to consider are: first, the charge and discharge cycles, to calculate the number of complete cycles of the battery. So in this case, we have decided to use a simplified version of the rainflow methods. So this algorithm allows you to separate the charge and discharge peaks that happens during battery operation in order to determine when a complete cycle has been completed. So once the number of cycles has been calculated, taking the specifications given by the manufacturer, the percentage of degradation is calculated. Also, we take into account the damage due to vibrations. For the degradation of the battery due to the vibrations during its operation, I confess it's not possible to find conclusive information now at this moment, but it's been decided to use also the rainflow method again to calculate the stress cycles to which the battery is subjected, taking into account the intensity of the vibrations and accordingly applying a small degradation factor. So also we take into account damage due to extreme temps. So, and in this case, it's very interesting because for the degradation happening due to the temperature of the battery, it's been decided to differentiate between the instantaneous degradation at room temp or during operation. So on the other hand, the long-term degradation that occurs due to the variation of temp during the charge and discharge cycle. So first we distinguish what's happening at room temp and what's happening when we apply the cycles of charge and discharge. So here on the right side of the screen, we see a graph of the degradation of the battery at 40 degrees of temp, and depending of the number of charge and discharge cycles. So as it's logical to think, as the number of cycles increases, the remaining useful life decreases greatly. So following with this example, the machine learning models developed are powered by data collected from different systems, different signals from the battery parameters. So among them, we have taken, of course, the battery specification, the battery voltage and currents, the cell voltage and current as well, the temperature and the charging status, and of course the power when charging and discharging. And of course, the algorithms use this data to evaluate the health and the performance of the battery. And the difference between the existing machine learning models is that instead of just collecting data and analyzing the battery data, this framework from City is designed also to take into account vehicle data as a whole system. So this is important because the variables that influence the life of an electric bus battery includes details like the air conditioning system and outside temp. So the more granular the data or collection is, the better and more accurate the prediction will be. And now arises the following question. So can we rely on battery management systems as called as BMS? And the answer is absolutely not. Why? Because battery manufacturers assume very standard cases, and these standard cases are not fully representative of real cases, of edge cases, or unexpected use conditions. So, although the battery BMS is capable of transmitting sensor data and diagnostic issue codes, there is still a gap between what this type of data can tell fleet managers and what actually is happening in a crashing pad, for example. So it's the real life. So for this reason, it's essential to consider the battery in the broader context of the other vehicle components and how these interact and affect each other within the broader system. The broader system is, of course, the vehicle. So on this page, on the right side, we see user applications related to predictive maintenance. We see the useful life of the vehicle, hours until the next maintenance operation, the necessary spare parts, so etc. So thanks to predictive maintenance, you can know in advance based on the dates of or mileage when you should replace wearing components such as the starter battery or the brake pads, receiving, for example, reports whenever there are signs of malfunction of crucial components with artificial intelligence models for detection. So remote diagnostics is like having in situ how do you say, the most advanced diagnostic equipment installed in each of your vehicles operating at all times in every time. So you can view active error codes, what we call as DTCs, and personalize and custom alerts on your vehicles based on the severity with visibility into key maintenance metrics by comparing history and checking sensor behavior in real time with messages, emails, or notifications. So with automated maintenance plans, vehicle mileage and run times are automatically recorded. So you can receive alerts when your next service is due. Additionally, your plans can also be automatically adjusted based on faults detected by remote diagnostics and predictive maintenance. It's also possible to monitor and control vehicles all in one place in real time and on the same map, as we see on the screen. Consumption and other metrics and alerts can be anticipated based on fleet configurations. And of course, these are the technologies that allows us to establish also a fair scoring system to ensure that drivers make our fleet safer and more efficient. So it's possible through a driver identification add-on. So a complete visibility of the fleet performance can be obtained in any type of operation. So even a specific fleet training needs can be identified by being able to uncover driver performance to help minimize wear and tear of components in their vehicles. And now, before changing gears to a smart city, please to the audience, is there any question, any comments, anything from anybody?
There's a question in the chat from Jose Javier Larrañeta.
Okay.
Do you analyze even to small component behavior level or just subsystem level? So this was a question that was done some time ago.
Okay, perfect. So thanks a lot to the question. So it's really interesting. Of course, the predictive models, the ETAL twins, it can be applied to any components independently on the size. So it doesn't matter if we talk about a complete system, a complete machine, a complete vehicle, or even a specific component. So we have seen the example, the batteries, but even we can go down and deeper to the case of a small cell or even components made by mechanization, made by forge, made by profiling, by any methods you can imagine. So it's possible to study the behavior, not only the performance of the component or the parts. I think about the cases of the electronic industry. So every essay, every performance are previously simulated with tools like can be MATLAB or any tool that can be used by our own. So it's very interesting points, and thanks for the question. So as a summary, any component independently on the science can be analyzed, simulated, and what's most important to be integrated into a further system. Anything, anything else from anyone?
There's another one from Javier. So for the others, just feel free to open your mic if you prefer that, or I'll read them from the chat, whatever you prefer. So from Javier Serrano, what about the reliability of the sensors themselves?
Okay, so now at this moment in the 21st century, the reliability of the sensors is quite high. Of course, depends on the environment. So they are processors, they are IoT devices prepared, with IP specifications in the fashion of IP67, 69, so specifically protected against the environments. And of course, is not the same an IoT sensors applied to the civil industry or to the army example. So as we can imagine, the specifications from the uniforms are much stronger and much more demanding. But now we can assume that the reliability, the sensors to capture data, physical variables like the temperature, pressures, etc. are quite reliable, and we can rely and we can trust on the information supplied by these kind of sensors. And of course, it's very important and very interesting this point because the quality of this data it's very important for the deployments of the simulation tools and the deployment of a digital twin. So if we don't feed up a digital twin with truly information, truly data, the digital twin outputs can be maybe erroneous, and well, the performance of the DT can be not perfectly matched to our needs.
Thank you, Santiago. There's a new question from Jose Javier Larrañeta. Is it worthless, the additional effort in systems development to reach component level?
Okay, so thanks a lot again for the question. So the development of systems, from my standpoint, is very important because we relied on tools about simulation, about digital twins, and as we'll see on the final slides, we can comment the true advantages of the DT tools. So I am really pro the development and the design of systems, thinking and also bear in mind the approach of MBSE. So every system, every components can be simulated previously, and for me it's really worth the effort. And with the current tools, so they are very easy, very quick, and we can launch not dozens, hundreds, but thousands of simulations in real time, very quick. So I encourage you to invest in the simulation of systems and the simulation of almost everything, from the layouts of plants, from the design of components, the integration of systems. Imagine the case, for example, in the aero industry, the connection between all systems, so it's paramount to get the simulation previously.
New question from Javier Serrano. Do existing sensors cover all type of relevant credible failure modes for critical components in an appropriate manner? Size, reliability, etc.
Okay, so it's really complicated, difficult to find out only one sensor covering all the data and variable we need. So the most feasible approach is to get an array of sensors to measure data from, a database, to get information about pressure, temperatures, environmental conditions in the case of a vehicle, speed, GPS, location, position, RPM, etc. So I think it's better to rely on specialized sensors for not for each variable, but not trying to compile all information using only one set. And if we use only 2 or 3 sensors, for example, I imagine the case in an industry, machinery, we can think about welding machines, welding stations, mechanization stations as well. So we can rely only on in 4 to 5 different kind of sensors, and we get all the information regarding the performance and the output of this installation. So with all this data, reliable data, we can come up the simulation, the digital twin, and foreseeing what could be the future in our industry. So for me, it's worth to invest and to install different kind of sensors all over the installation, all over a vehicle, etc.
Thanks, Santiago. That's the last question we have in the chat for now.
Okay, so thanks for the question. So now we can go on. So changing gears to smart cities. And I would like also to mention the importance of the digitalization in such a specific area like a smart city. So with the digital twin, as always, and proper simulations, we can test and train the following. First, the traffic control, avoiding pointless traffic jams and hotspots. So we can model the best routes for transit and evacuation in case of emergency for all road users. So we can take advantage of all sensors embedded in vehicles, radars, lidars, cameras to road inspection and see the status of signs, horizontal markings, and even the quality and the degradation of the pavement. So here, a digital twin can not only detect but prevent the evolution of cracks, bumps, and ditches on the asphalt in order to prevent accidents, but also we are able to have a complete up-to-date model of our environment in real time. So we're able to get accurate to the slightest detail models of our streets and its real status. The second, the IoT communications from vehicle to vehicle, so what's called as V2V, and from the vehicle to everything, V2X. So the V2V and the V2X will be instrumental to share billions billions of bytes of information in the clouds and be knowledgeable about what's happening ahead of us and around the corner. So our vehicle can transmit and receive information in the same way to be updated about any danger or simply the best routes to go from a point A to a point B. Of course, using the virtual worlds, we can perform the self-calibration of our ADAS systems and sensors thanks to the IoT and information from other vehicles. So now it is not needed to stop a vehicle or a fleet for some hours in a workshop to recalibrate the sensors with specific tools. So we can communicate with other vehicles and the infrastructure to get information and compare it with information we are getting by ourselves. So if there is a match, our ADAS calibration is okay. And if not, we can take the surrounding assets information as a pattern to recalibrate our sensors online and in a matter of minutes. So online and in situ. So this is especially important in elements and devices in our car, helping to run in cities and open roads. The remote driving of vehicles in urban areas, so we'll see later, and open roads now is a reality. So made possible with IoT connection and the power of the simulators and the digital twins, replicating the environments, supporting an extra low latency. So imagine how businesses can grow managing remotely and safely a fleet of vehicles. So in the fashion of taxis, vans, small trucks. So we'll see later, I see. And finally, the erection of real-time, the ETAL maps from data taken from vehicles and UAVs, drones, also are possible to better plan the smart cities and factories of the future. So I insist of the fact of gathering information from the real world and combining it to virtual data generated by our ETAL twins. So all in all, they contribute to better training of virtual models. So as stated before, at the beginning of this conversation, so I would like to continue giving some examples of how we can contribute from the city engineering group to the digitalization of a smart city. So I present you the project's road digital twin, and in this case, we use the vehicle's ADAS systems and sensors as elements to capture data and information on the roads. So I mean, cameras, GPS sets, and lidars essentially. And to do this, we make extensive use of artificial intelligence to detect the status of key assets on our roads, such as traffic signs, road markers, traffic lights, cracks, and potholes in the pavement. So we obtain data and their status and the GPS position. So these elements are processed to have a structure and order data, and we analyze it via big data and artificial intelligence techniques and show the data to the end user on portable devices such as a PC, a tablet, or a handy. So this allows us to develop the predictive model about the evolution of the states of the elements of roads. So we talk about a digital twin about the roads. So we can see on our screen what could be next on our streets, on our city, and using as sensors the ones mounted in our vehicle, in your vehicle. So imagine the case as how many observers we can take into account running to and through. Thousands of cars can provide pristine information and become observers of what's happening in our environment. So all these anonymous vehicles are a huge amount source of information susceptible to be dealt and analyzed to get a mammoth, a gigantic set of data to train predictive models to better to improve in short, in the short, in the mid and long term, so the condition of our cities to the benefit of safety and efficiency. So from my standpoint, it's really fantastic. So as a matter of example, here we can see the sensor structure we have used. We observe the radar, a GPS set, what is called now the GNSS, the camera, and two LiDAR devices. And on the right side of this page, we can see how the data is presented with the front camera and is virtualized afterwards to get a model, and the two LiDAR devices with a coverage of 360 degree gives plentiful information via an immense cloud of points. So vertically speaking, the field of view can reach -20 and plus 70 degrees of coverage. The next program is what we call the bus digital twin. So here we deploy a network of IoT sensors to acquire the most relevant data from a fleet of urban buses, from basic vehicle information parameters such as the engine or even the occupancy levels to driver data and their workloads. So making extensive use of artificial intelligence to extract true value from data. So it's important to note the importance of knowing the level of stress in the people. And as far as we know, A urban bus in the middle of a congested city can be a very harsh environment for everyone. So our approach is to know in real time the level of tension withstood by personnel at the wheel, and specifically to train these people in the best management methods to be sure the performance at the wheel remains high and able to tackle a traffic congestion. So we talk about a cognitive training for people and the ability to predict when and how the drivers are going to be overstressed. So with digital twins virtually replicating the bus, we're able to generate synthetic data to improve AI algorithms and establish the predictive bias of real systems. So we can follow analytical techniques or rely on data. And here we see a general scheme of the communications between different systems. So based on the cartography available, we generate a 3D environments, and over it, we display the behavior of model of the vehicle and also the pedestrians and the rest of open road users. So our system allows to simulate different entities at the same time in a coordinated manner, generated the synthetic data that can be combined with real data. So that's the power of a DT, the combination of synthetic data and real one. So complex algorithms of predictive maintenance and fleet optimization also can be deployed. So that's the vehicle sensors are integrated with the smart city ecosystem, and all the connected and simulated entities interact with each other. So we have discussed the importance of the connection via IoT of sensors and the simulation in virtual environments. So within the framework of this vast digital twin, our real-time simulator shows a very realistic graphical environment with perfectly fits a human-machine interface, so that multiple test grounds can be managed in a cooperative simulation framework. So another example, the Calyx to self-calibrate sensors in vehicles automatically and in real time. So here we acquire data from the vehicle system, the vehicle telemetry, and we connect it through V2X and the protocol of 5G with other vehicles and the infrastructure as well, in the fashion of traffic lights, cameras on gantries, etc. So if we compare the data captured by our own vehicle, and if it's a coincident to the information transmitted by other vehicles and the infrastructure, so the likelihood, the probability that our sensors are well and okay is very high. And if not, we can self-calibrate our sensors with information transmitted by third parties. So we all agree at this point that sensor accuracy is key. And now static calibration can take up to 2 hours of downtime. So with the technology we show here, the calibration of sensors takes a maximum of 5 minutes. In addition, we can carry out continuous dynamic calibration by comparison constantly with other road users. So in this particular case, we focus our attention to the ADAS system destined to assist us in an emergency braking. So we can see the relationship and the connection between other vehicles and infrastructures as well. So with information, with our own vehicle safety suits. So it's, from my standpoint, a clear example of collaboration between systems. You know, smart systems talking between themselves and each other. So delving into the case of the sensor self-calibration, I show you the main architecture for the communications network. So linking through the communication gateways with intermediate and final nodes through artificial intelligence. So this real-time communication with databases and data outputs to the user's HMI devices. And in this case, as we talk about deeply about automotive, the main protocols are CAN bus and Ethernet. And also we are participating in the projects we call the European Eco-Mobility, in which at City we are developing a traffic manager for a smart city. So with the data captured by the vehicles with the help of their ADAS systems and infrastructure through V2V and V2S communications with 5G protocols, three-dimensional maps of the environment. So all this information we gather all the items to generate the traffic manager. So we developed predictive models to streamline the circulation of a large city and thus avoiding incidents, traffic jams, accidents. So making transit between point A and point B of destination more agile and faster. So significantly improving the user experience and contributing to a greater eco-sustainability. So as we have seen, we take advantage of vehicle sensors to capture data and images from our own environments to get an exact replica, virtually speaking, of what we are seeing. So next step is to get a virtual and mapped environments so we can use for these tasks graphic engines such as Unreal or Unity to simulate our smart city. And then we can put over a fleet of vehicles. So at this point, it's very important to remark our approach is to provide the vehicles with intelligence, with the capacity to decide how to go from a point A to a point B, depending on incidents and depending on traffic. So the paths are not predetermined in advance. So the point is to deploy smart models, smart vehicles able to decide in situ and online the best routes. So the best, for example, mean speeds to avoid the red lights on traffic lights, the best parking lots, and all this is going to be achieved with extensive use of communications between land vehicles and, that's very important, aerial platforms. So what we call as UAVs or drones in short. So cars will be in their with their own set of intelligence to decide and in the near future could rule the smart city. And as we talk about the communications between assets and vehicles, also I would like to mention the need to secure the communications. So it's not the same the messages transmitted and received by commuters compared to the communications between the military or police vehicles. So we all agree that strategic vehicles, such as from the police and the armed forces, needs a protocol of protection of cybersecurity and encryption much stronger than what's needed for civil applications. So we are also implementing this added value layer of cyber protection, backed even by blockchain, to get a perfect traceability of the communications and links. So this is, in my opinion, this is the perfect match for a smart city. 5G communications, connectivity, V2V and V2X, artificial intelligence, predictive models based on machine learning and deep learning, cybersecurity, and blockchain. So that's the perfect approach. And we even allow ourselves to advise you on the best driving strategy. So in this concept of city, we can deploy models for remote and autonomous driving. And as we talk about remote driving, we are developing just that. So the remote driving. So imagine the case that you are peacefully seated at your office or home and you are able to drive remotely a real car in the middle of the street, in the middle of a real city or highway, and in the middle of real cars and real city and road users, bikers, pedestrians, skaters, and so on. So now at City, we take care and are in charge of the communication with the sensorized vehicle, all the ADAS suits and control actuators, the remote driving station, and the communication with the control center. We are also developing a simulator impersonating the real car. So the communication protocols we use are MQTT and UDP. And on the right side of the screen, we see the basic architecture proposed at very high level, of course, for the communications between different subsystems, so that it's between the vehicle itself, the driving station, and the omniscient control center. So it's important to highlight the fact that it's resistant to general failures of communication, to the network, able to be working on even with poor communications, and allowing ultra low latency in information transmission, specifically referring to video signal and commands to control the vehicles. So please take into account that a latency in the region of 50 milliseconds at a speed of 75 miles an hour means the car runs without control for a time of 4 to 5 seconds. So now we're struggling to reduce the latency to 10-15 milliseconds to minimize to the maximum extent the distance the vehicle could run uncontrolled. So the main advantage of this approach goes to fleets of taxis, vans, small trucks, and so on. So one person, of course, cannot manage more than one vehicle at the same time, so it's obvious. But one person can be switch on or switch off from one vehicle to another without elapsed times, so in a matter of a few seconds. And this, in my view, contributes to increase the efficiency of operation of vehicles and decrease, especially in transportation of goods, the legs with the truck fully empty. So in one word, so remote control of vehicles is the threshold of autonomous driving and is perfectly matched to the management of a smart city from the traffic standpoints. So we are going to make subset two type simulators linked to the vehicle. A basic one for the first integration and trials of systems, and a complete one showing a complete interconnection and a very realistic simulation. So, and finally, and just to finish and to close this session, we're going to mention the main benefits of virtual twins. Of course, quality, safety, speed, reliability are among the best one and the most important ones. Benefits of simulators and DTs, digital twins. So we can increase the quality of products and process designs, as it's possible to correct initial errors from the outset. This is really important, as we can launch a product to the market or commission a machine in a faster way. So the human and machine can be introduced in the loop to assess all the scenarios. So with this approach, we give the simulators all features to work in unison and none in a separate and less than useful way. All assets simulated are safer, so we can detect from the outset any kind of failures in the design and the day-to-day working operation. So in one word, the prediction of a long life. And the last message, especially for the financial areas, thousands of simulations can be performed without the need of huge investments. So the advantage of simulators over the real essays based on errors and redesigns is more than obvious and evident. Okay, ladies and gents, that's all from my side. So thank you so much for your kind attention. And if you have additional questions, of course, I will be more than happy to discuss openly. So thanks a lot.
Thank you, Santiago, for the presentation. So I don't see any other question in the chat. I don't know if anyone else wants to ask something or maybe make a comment or any contribution to this great presentation. Feel free to use the chat if you have any question.
Maybe we can imagine the cases from the industry standpoint, from a smart city standpoint. If anyone has any issue regarding a vehicle fleet, a machinery, the layouts of the industry, the operation of different systems from different suppliers.
Okay, I think we can close here the presentation then, since I don't see any question in the chat. some people thank you personally as well. Thanks everyone for attending. Just as a reminder, the recording of this presentation will be made available in the IAE Symposia website. So you'll find there the recording. Have a nice day, everyone.
Thank you very much to everyone. Thank you. Take care.
Okay, thank you.
Thank you very much.